Hey everybody, really been missing you. Miss seeing you in class every day. Just miss being on campus, but I'm eager to get back in the fall or over the summer. And honestly, I think that I'm eager to finish the semester. I think that working online is probably a lot harder than working in class. So just a couple of things before we get started. Just want to remind you that I am dropping your lowest quiz grade, and then I'm also dropping your lowest exam score. I understand that online instruction is not what you signed up for, and that it's often more difficult than face to face. Depending on the kind of student that you are and the way that you learn, it can be quite a bit more difficult. So I hope that that helps you in the class some. I know it does help many of you in your averages. So that's not something that I normally do, but I'm doing it in this case just because, it's special circumstance. Uh, so I put a new grade calculator on the website. You can take a look at that and put in your grades for extra credit for your exam 4 and your final to figure out what it is that you need to make on the final in order to make a certain grade in the class. This exam, which is on Monday, it'll be on Moodle, just like exam 3. You'll need to use Respondus, the lockdown browser, and the webcam, so make sure that that's all in working order before you get started. It'll be during the normal class time. I'll probably give you 15 minutes on either end, and I'll also probably give you a little bit longer time. So let me know if you have another class that meets right after ours and that's a problem for you. So I'll send that announcement out on Monday morning, giving you the time, but let's see, it'll probably be from 10:30 to noon, and I'll give you, an hour and 15 or an hour and 20 minutes to complete the exam, but it'll be a normal length exam. I don't know if you've caught on to this, but the last exam came entirely from old exams. So I suspect that many of you have noticed that, and that'll be true for this exam too. Um, just because it's not what I would normally do, but we're in a different kind of situation. I have a handful of questions from people, but first I want to just go over the topics that'll be on the exam. A good way to understand the topics is to look at these different categories. It is just chapter 7 and 8. So for the screencast, you can see all the different topics that you have. And the way I do this is I have a certain number of questions from each of these topics. So I would expect to see every single one of these topics on your exam. As you see, there are a lot of different topics. I mean, there are 19 different topics and only 28 questions. So you'll have probably at least one question from each of these. In chapter 7, it is broken down largely into mirrors and lenses. And then we have a couple of other things with the atmospheric phenomena and the aberrations thrown in there as well. You need to understand how to calculate the image or object distance for certain mirrors for the magnification. You'll need to understand how to work with those equations and look at those problems to see how how to work them. We'll look at some of them as well. What will really help you on this exam is to know your ray diagrams and to know them really well. Not that I'm going to make you draw a ray diagram. I'm not, though I will ask you likely a question where I show you a number of different rays and I ask you which is correct or incorrect. But knowing the ray diagrams and knowing the types of images that are formed by the types of mirrors or lenses will really help you in some of the other questions. So in chapter 7, that's the big thing that will help you. The other thing in chapter 7 is to always watch your signs. And in fact, in chapter 7, for those problems, I would just get in the habit of writing positive or negative. I know they don't usually put a positive sign on a positive number, it's just assumed, but it will help you to remember to write a negative when you need to write a negative. And with we'll come back to that, but those two things, knowing your ray diagrams and then knowing your signs. And then in chapter 8, chapter 8 is really 3 different topics, or really 2 different topics, but one of those is split into 3 different parts. So there's interference and phase, and we'll look at some questions about that. And then the double slit, the single slit, and the gratings are all very, very similar, where we're talking about combining light of the same wavelength but at different phases, and then looking at the resulting interference pattern when I get constructive and destructive interference. So chapter 8 is first interference in phase, sort of a basic understanding of what goes on when you combine light with a different phase, and then the application of that, which is in double slit, single slit, and gratings. You'll find that double slit and diffraction gratings are identical in the way that they appear to you mathematically, and single slit is really similar, but it's different in the way that it presents mathematically. So just be prepared for that. Practice, practice, practice. Practice those old exams. That's your best way to do well on this exam. And then finally, the Fresnel diffraction, which is really just a special case. Often I don't even have a question about that. You may or may not. It's just the circular diffraction pattern. So let's look first at the questions that students have given to me. Okay, the first question was for this one. This is Spring 18, Exam 4. In fact, you'll only be looking at Exams 4, unless you go further back, we'll only have 3 exams. And the student asked for this problem number 16, how come for D you didn't have to use 1 over 0.2 millimeters? So on these problems, let's just take a look at it. The student asked, why didn't I take the inverse of this? Now, to find D, in some cases, if you're using the diffraction gratings, you take the inverse of the slit spacing. But if you're dealing with a double slit diffraction gradient or a double slit pattern, then the distance D is given in the problem. So I understand that this is a double slit problem because it tells me there are 2 slits. And so physically you have a barrier with 2 breaks in it, so 2 holes here and here, and the distance between those is going to be D, and in this case D is equal to 0.2 millimeters. So D is 0.2 millimeters. That's 0.2 times 10 to the minus 3 meters. And I'm given some other information. I'm told that lambda is equal to 650 nanometers. Make sure in chapter 8 especially that you always convert your units to SI units. You'll never go wrong in the SI system. In some cases you don't need to, like in chapter 7, often you don't need to change your units, but in chapter 8 it's very important that you do so. I'm given some other things as well here. I'm given this, which is L, so L is equal to 5 meters. And then I want to know how far away is the second bright fringe. So in a double slit, let me rewrite this a little bit. So in a double slit where I have my slits right there, and then this is my screen, and I get a diffraction pattern that looks like this. And the diffraction pattern occurs because I have 2 different light rays that are traveling different distances, and when they arrive at a point they may be either in phase or out of phase. They're in phase when they make a bright spot, and they're out of phase when they make a dark spot. This is my distance D. This is my distance L, the distance from the screen to the slit, and then the order number is given here. So this is M equals 0, this is M equal 1, and then this is M equal 2. 0, 1, 2. We'll find that's different for single slit, but if I'm dealing with a double slit or a diffraction grating, that is my order numbers. And I help you out with that on the equation sheet because I give you the available order numbers. So take a look at that equation sheet and make sure that you understand what the order numbers mean. So I want to know how far is the second bright fringe, and that distance is going to be the distance from here all the way up to here, and I'm going to call that y. So the way that I do this is I have to first calculate what this angle will be, and so I say d sine theta equals m times lambda, and so I want to find theta, so I say theta is the inverse sine of m lambda over d. I'm going to pause here for just a second. I'll calculate. Okay, so when I do that, I get 0.37 degrees. And then I want to find what is the distance y. Well, notice here that I have a triangle, and I'm looking for this leg of the triangle, y, and that y is equal to L tan theta. And so that's 5 meters times the tangent of 0.37, and that's equal to 0.033 meters, and so that's 3.3 centimeters. Let's look at a single slit. I think I have one on this exam. By the way, if you're looking at old exams and you start seeing stuff about sound, I like to do the sound chapter in the second semester, but we're not doing it this semester. Oh, let's see. That's diffraction grating. Well, let's do a diffraction grating because they're really similar to double slit. The only difference is that for a diffraction grating, in order to find D, you have to use this quantity, which is the lines per centimeter or the slit spacing. And in order to find D, I just take the inverse of that. Now in the previous problem I didn't do that because I was given the distance between the slits. But in this case I'm not given the distance between the slits. For a diffraction grating I'm given this slit spacing, which is the inverse of that. So this would be in centimeters, and so in order to find D I would say 1 divided by 2500, which is 4 times 10 to the minus 4 centimeters, which is 4 times 10 to the minus 6 meters. Get really good at converting those metric prefixes in your head, okay? It'll save you a lot of time. And then, if you want to know the angle, well, it's exactly the same as what we were doing before. D sine theta equals m lambda. I have D now. I'm looking for theta, so I say theta is the inverse sine of m lambda over D. M is 1. It's the first order maxima. Lambda is green light. It's 520 nanometers. Divided by D, which I have now, is 4 times 10 to the minus 6. And I find the inverse sine of that. It is whatever it is. I'm not sure what the answer is, but it's one of these. Oh, by the way, if you come to an answer and you get an error, that means that there is no first order maximum. Let me show you why. Imagine that I have a double slit. The pattern will extend out until the angle exceeds 90 degrees. So if I imagine that my two light rays have to travel this angle in order to get to wherever they're going. However, if that angle is larger than 90 degrees, that means that the light is actually just going here. And if that's the case, if the angle theta is larger than 90 degrees, then that means that there is no first order maximum. And so the way that would work out in your calculation is you would get an error. If you get an error, then you know that's the answer, that there is no first order maximum. Okay, I want to find a single slit. Let's see here. Okay, so this is a single slit, number 16. Where I know that this is a single slit because it doesn't talk about two slits or diffraction grating. I just have a single slit with a certain width. And the pattern looks really similar with the single slit, that you have light that originates here and then it forms a diffraction pattern with a bright spot and a dark spot and a bright spot and a dark spot. So it looks really similar to what we have with double slit and diffraction gratings, but mathematically it's a little bit different. For this single slit, the diffraction pattern is defined by this equation. A sine theta is equal to m lambda. Here, A is the slit width. And unlike with double slit, where it was the distance between the two slits, this is actually the width of that slit. So a single slit, whereas a double slit has tiny little narrow openings, a single slit has larger openings. For example, there is the occurrence of a single slit diffraction in your eye, because your aperture of your eye is fairly large. Anyway, so that's one difference. And the other difference is that M does not refer to bright spots. Instead, it refers to dark spots. Now, I tell you this in the equation sheet. So if you forget, just look on the equations like, oh, The single slit has dark spots. And so the order numbers are a little bit different. Here, this is m equal 1, this is m equal 2, and on and on. This is 1, this is 2. So unlike for double slit or diffraction gratings, there is no 0th order. Okay? So that's really the only difference there, but it works out a lot the same. A student asked about number 15 on exam 4 in spring 16. Yeah, so this gets back to our interference section. So in chapter 8, looking at interference and phase, and I would expect, a couple of questions about this. Two electromagnetic waves have a wavelength of 3 meters. Remember, the wavelength is the distance from here to here. So that tells me that's 3 meters. They are coherent and initially in phase. That means that their wavelength doesn't change, it's coherent, and that they're initially in phase. To be in phase means that their peaks and their peaks line up, and their troughs and their troughs line up. And so if I was to add these two together, I would have constructive interference. Okay? But what happens is these two light rays travel different distances. One of them travels 4 meters, and then one of them travels 2.5 meters to the same point. So one of them travels a shorter distance to the same point. And now I want to know, what do I observe when those two light rays get here? One of them has traveled 4 meters, and one of them has traveled 2.5 meters. The path length difference, I'll call that PD, is equal to 4 minus 1.5 meters. So that means, 4 minus 2.5, which is equal to 1.5 meters. So the path length difference is 1.5 meters. I want to express that in terms of wavelengths. Because the wavelength is 4 meters, 1.5 is some fraction of 4, and really the only, actually no, I'm sorry, that's not the wavelength. The wavelength is 3 meters, so this is equal to 1/2 of a wavelength. These two light rays are out of phase by 1/2 wavelength. Out of phase by 1/2 wavelength. And so if I imagine drawing my two rays, the second one is going to start at 1/2 a wavelength into the first one. So if you imagine this is where my ray starts, and then this is where my wave ends, my second wave starts here. It starts offset by 1/2 wavelength. And so when these two rays combine, my troughs and my peaks are going to line up, and my peaks and my troughs are going to line up. So that is destructive interference. That when those two light rays come together, there's not going to be anything. So that is going to be a dark spot. And that's physically what happens to the light with double slit, with single slit, and with diffraction gratings, that in the bright spots, I have two light rays that are either 0 wavelengths out of phase, or 1 wavelength out of phase, or 2 wavelengths out of phase. But at the dark spots, they are going to be some integer multiple of 1/2 a wavelength, 1/2 a wavelength, 3/2 of a wavelength, 5/2 of the wavelength, and on and on. Okay? Okay, I had another student who asked a very similar thing about the path length difference of waves and whether to know if it's constructive or destructive. With the path length difference, let me write this down again because several of you have asked. If PD is equal to 0, 1, 2, 3 wavelengths, that is constructive. And PD is the path length difference, which is really just subtracting one path length from the other. And if PD is equal to 1/2, 3/2, 5/2, etc. wavelengths, and that is destructive interference. Those are sort of the two guiding rules for that. If you're offset by 0 or a whole number of wavelengths, that is constructive. Let's look at that, by the way. Let me write something over here. So if I'm one wavelength offset, my wave starts here and it goes there, and so my second wave would start here. See how these peaks and troughs, they line up together? That is constructive. And I am offset by one full wavelength. But if I offset by another half a wavelength over to this point, now my troughs and my peaks are lining up, and so that would be destructive interference. So it's all about the path length difference, and I would expect to see some questions that are similar to this one. Okay, another student asked me for question 17 from spring 2011. Usually warn people about going back this far. I mean, a lot of the questions are still really good. It's just sometimes I might have shifted in how I teach it or how I assess it. But this is a fine question. So this is a single slit, and I want to know what is the slit width. So that is, I want to know what is A. Here's my angle theta, here's lambda, here's m. So I like to go through and write down these just in the problem, write down the different things. So lambda is equal to 546 times 10 to the minus 9. Theta is equal to 0.092 degrees. A is what I want to know, and then M is equal to the fourth dark fringe. Okay, and remember with single slits, A sine theta, the theta is for the dark fringes, not the bright, and that's different than it is for double slit R diffraction gratings. And then I'm solving for A, so A is equal to M lambda over sine theta. And so M is 4 times 546 times 10 to the minus 9, because it was nanometers, divided by the sine of 0.092 degrees. You'll never need to be in radian mode, by the way. I'm going to pause this. Okay, when I do that, I get 0.0014. Oh, look, these are all in millimeters, so I have to bring that over 3 spaces, and so A is going to be the right. Oh, wait, no. No, that's right. A is going to be 0.0014. Let me do say, actually, that sometimes I'll ask you how wide is the center fringe. That's not what I was asking you here, but if I ask you how wide is the center fringe, or the center bright spot, then that's the distance from here to here. Okay, so, but I want you to recognize that if I were to solve for y in the way that I did previously, that would only be from there to there. And so if I asked you for the width of the central bright spot, then I would have to double that value for y. Okay, you might see some problems like that in some of the old tests. That was actually not the question that they had asked. They had asked for question number 17. So let's go to that one. I'm sorry. That was still a good question. Oh, yeah. So this is another interference question. Largely, that's what I've been getting are questions about interference. I hope that your mirrors and lenses are up to date. So make sure that you're spending time on that as well. So for this one, I have 2 light rays. Both of them originate here, and they travel. One travels this distance and then back to here, and then this one travels here. So one travels a distance of 50,000 meters. The other one travels a distance of, well, I don't know. It travels an additional distance of, I don't know what it is. And so I want to know, what is this distance here in order for me to get destructive interference here? So what I know is that for destructive interference, the path length difference has to be some half of a wavelength. A half, 3/2, 5/2. In this case, I'm looking for the minimum distance. So that path length difference has to be a half of a wavelength. Because my wavelength is 600 meters, then the path length difference has to be, well, 300 meters. So one of these rays has to travel an extra 300 meters more than the other ray. So you might say, well, the answer is 300, but you would be wrong because the light ray here travels this distance and then it comes back and travels this distance. So this distance actually is to be 150 meters because it doubles back on itself and comes back. And when it comes back, it combines with this wave, the one that traveled the shorter distance, give you destructive interference. If you know anything about reflection and the phase change that occurs in reflection, you would know that there actually is a phase change when a light ray reflects off of a surface, but we don't really talk about that, so we just assume that there is no phase change. Okay, so that's what that sentence means, but it actually becomes a little bit more complex than that. Okay, somebody asked about the D in D sine theta equals m lambda. Just reiterate here, in d sine theta equals m lambda, that is the distance between the two slits. And so for example, let's see, there must be a problem here somewhere. So for example, in this one, this is spring 11 from exam 3, two slits are separated by a distance of 5 millimeters. That is my distance d, and it's equal to 5 times 10 to the minus 3 meters. Nothing weird going on about d sine theta equals m, about the d and d sine theta equals m lambda. Now, if you're dealing with a diffraction grating, it is a little bit more complicated. So with a diffraction grating, you use the same formula, d sine theta equals m lambda. But with a diffraction grating, you have to take an extra step in order to find d. D is the inverse of this. See, this tells me that in 1 centimeter, I have 12,000 lines. I have 12,000 of those lines. But really what I'm concerned about is this distance. And so in order to find that distance, I don't want to know the number of lines per centimeter. I want to know the number of centimeters per line. So I would say 1 over 12,000, and that'll be centimeters per line. So if that sort of dimensional analysis helps you, then by all means remember that. So then I would find, well, what is 1 over 12,000? Take the inverse of that, I get 8.3 times 10 to the minus 5. And don't forget, that's in centimeters, so I'd go 8.3 times 10 to the minus 7 meters. Okay, so that's probably what you were asking. I forget who asked that question. But when you're finding D for a double slit, it's fairly straightforward. It's just whatever I give you. But you'll probably have to change it to meters, okay, because that'll probably give you in millimeters or even microns. But if you're dealing with a diffraction grating, then you have to take the inverse of that slit spacing. Okay, let's just spend a few minutes looking at some of the other stuff from chapter 7. So I didn't really get any questions about that, but they're important. I think that we dealt with this a little bit last time in the last help session. But really you need to spend time studying the old exams. So let's just say you're going to have a question like some of these, like number 5, where I give you a lens or a mirror, and I tell you to calculate something about that. And it might be a little bit tricky in the sense that you're going to have to know what kind of lens or mirror is being used. And so, for example, this is a lens, and I don't tell you what kind of lens, so I don't tell you if it's convex or if it's concave. That's an important thing to know because I know convex lenses have a positive focal length and concave have a negative focal length. And so here a real image forms, that's going to tell me right away that this has to be a convex lens because a real image has formed. Um, then I can go a little bit deeper and I say, well, my object distance, that's P, is equal to 50 centimeters. Notice I don't have to convert to SI in that. A real image is formed at 40 centimeters. And a real image is always going to have a positive image distance. So because it's real, I know that has to be positive. If I said a virtual image formed at 40 centimeters, then that would change the problem immensely. Then Q would not be positive, Q would be negative, and likely I'd be dealing not with a convex lens, but I'd be dealing with a concave lens, so my focal length would be negative. So I can change the question a lot in that way. Also, here it says that the image is on the opposite side from the object. And remember, for lenses, if the image is over here or if the object is here and this is the image, this is going to be a real image. If this is the object and this is the image, then that's a real image. However, if the object is over here and the image is over here, then this is a virtual image. And remember in the last help session we talked about this, but virtual images are always upright. They're always upright because m is equal to negative q over p. A virtual image has a negative q value, a negative image distance. That means that m is going to be positive, and a positive m is a upright image. Okay, and so this question, I just want to know what the focal length is. And so this is actually a fairly straightforward question. I have 1 over f equals 1 over 50 plus 1 over 40. What's the common denominator there? 200, I think. Anyway, you can solve that on your own. So you might have a 2-lens system. Make sure you practice those. It's really just like 2 1-lens systems. You probably will have a 2-lens system, in fact. So practice those. So spherical mirrors aren't in this. So I know that I said just exams 4, but you really need to look at exam 3 as well. So make sure that you're getting those spherical mirrors. All right. Don't forget too that you're going to see chromatic aberration or spherical aberration, and then you'll also see those atmospheric phenomena. I think that was the mirage and the sunset. The sun actually sets before you see it set because of the bending of light by the atmosphere. Okay, all right. Review chapter 7. We haven't spent much time on it. Make sure that you review that. And we'll stop there. Hey, listen, if you have any additional questions, you did it pretty early, but if you have questions, I can address those in video form or just over email, so you can send me those questions overnight, and I'll get them, several hours before the exam, or I can even address some this evening if you send them to me. Okay, I think we'll stop there. Have a good night. See you.